In the quiet expanse of the South Atlantic, a subtle secret lies hidden beneath the waves. Satellite measurements, those silent eyes orbiting our planet, have revealed a region where the pull of gravity is inexplicably weaker than anywhere else on Earth. This is not a tale of myth or fantasy, but a genuine scientific puzzle that has drawn the attention of geophysicists, oceanographers, and curious minds worldwide. The question looms: why does this patch of the planet tug less on our bodies, our instruments, and even the very water that laps its shores? To understand the gravity anomaly, we must first revisit the fundamentals of gravity itself. Sir Isaac Newton taught us that every mass exerts a pull on every other mass, a force that diminishes with distance. Modern physics refines this with Einstein's curvature of spacetime, yet the measurable effect on Earth's surface remains a direct function of the planet's internal distribution of mass. Mountains, dense rock, molten magma, all contribute to the local gravitational field, creating a complex tapestry of highs and lows. The first hint of an oddity emerged in the late 1990s, when the European Space Agency's GOCE, Gravity Field and Steady-State Ocean Circulation Explorer, mission mapped the planet's gravity with unprecedented precision. Scientists noticed a subtle dip, a few milligauss lower than surrounding areas, centered near the mid-Atlantic ridge, but offset to the west. This deviation, though minute, roughly the weight of a feather on a human, was statistically significant, prompting a wave of investigations across continents. One early hypothesis pointed to the oceanic crust itself. The seafloor spreading that builds the Atlantic is a continuous process of basaltic lava cooling and solidifying. If the newly formed crust were somehow less dense, perhaps due to higher temperatures or trapped gases, it could produce a local gravity deficit. Ocean drilling programs, such as the International Ocean Discovery Program, retrieved core samples, yet the density measurements aligned closely with global averages, leaving the mystery unsolved. Another avenue of inquiry turned upward, toward the mantle beneath the anomaly. The mantle, a vast layer of silicate rock, convex slowly, transporting heat from the core to the surface. Seismic tomography, Earth's equivalent of a CT scan, reveals variations in temperature and composition. In the region of interest, seismic waves travel slightly faster, suggesting cooler, more rigid material. Paradoxically, cooler rock should be denser, which would increase gravity, not decrease it, deepening the conundrum. A third contender emerged from the realm of water itself. The ocean's surface is not a uniform sheet, it bulges and dips in response to tides, currents, and temperature gradients. Satellite altimetry can detect these subtle sea level variations, which in turn influence gravity measurements. Some scientists propose that a massive, yet undetected, deep water eddy, a rotating column of less dense, warmer water, could mimic a gravity low. However, repeated surveys failed to capture any such persistent feature. In recent years, a more exotic explanation has entered the debate: the presence of a hidden mass deficit caused by a massive, yet low-density, mantle plume that has been partially eroded over millions of years. Mantle plumes are upwellings of hot material that can create volcanic islands like Hawaii. If a plume rose beneath the Atlantic and subsequently cooled, it could leave behind a cavity of lower-density rock, subtly reducing gravity in that locale. Yet the Plume Hypothesis confronts a stark obstacle: the absence of any surface expression. Over the past 70 million years, the Atlantic's western flank has been relatively tectonically quiet, lacking the volcanic edifices that typically betray plume activity. Geologists combed the seafloor for volcanic seamounts, magnetic anomalies, and sediment disturbances, but found nothing that could conclusively tie a plume to the gravity low. Complicating matters further, the gravity anomaly appears to be shifting, albeit imperceptibly, over decadal timescales. Newer gravity datasets from the GOCE, Gravity Recovery and Climate Experiment, mission indicate a slight migration eastward, aligning loosely with the direction of plate motion. This dynamism hints that the underlying cause may be linked to the slow dance of tectonic plates, perhaps involving subtle flexure of the lithosphere as it adapts to changing stresses. To probe these possibilities, an international consortium launched a dedicated research cruise in 2023, deploying autonomous underwater vehicles equipped with gravimeters, magnetometers, and high-resolution sonar. The mission charted a grid of measurements across the anomaly, revealing microvariations in the seafloor topography that were previously undetectable. These fine-scale undulations suggest a complex interplay of sediment loading, erosion, and perhaps even ancient impact structures buried beneath miles of water. Some team members propose that an ancient meteorite impact, dating back to the late Cretaceous, could have fractured the crust, creating a region of fractured, less dense rock. Impact craters on land often correspond with gravity lows due to the brecciated material they leave behind. Yet the oceanic environment erodes such features quickly, and no clear circular rim has been identified in the bathymetric data, leaving this theory tantalizing but unproven. Beyond the scientific intrigue, the anomaly has practical implications. Precise gravity models are essential for satellite navigation, sea level rise estimates, and even for calibrating the trajectories of interplanetary probes. An unexplained deviation, however small, introduces uncertainty into these calculations. Engineers at space agencies are therefore keenly interested in resolving the anomaly, ensuring that the foundations of our global positioning systems remain rock solid. The story also underscores a broader truth about Earth science, that even on a planet we have mapped in exquisite detail, hidden mysteries persist. The gravity anomaly is a reminder that our planet is a living, breathing system, constantly reshaped by forces that operate on timescales far beyond human perception. It challenges the notion of a static Earth and invites a humility that fuels scientific curiosity. Looking ahead, the next generation of gravity mapping satellites, such as the upcoming NGGM, Next Generation Gravity Mission, promises even finer resolution, potentially revealing submilligal variations across the globe. Coupled with advances in machine learning that can sift through petabytes of geophysical data, researchers hope to isolate the signature of the South Atlantic anomaly with unprecedented clarity. Whether the answer lies in mantle chemistry, hidden water dynamics, or a process yet unknown, the pursuit will push the boundaries of Earth observation. In the end, the place on Earth where gravity is weaker remains a subtle, almost poetic reminder that nature guards its secrets well. As scientists continue to peel back layers of rock, water, and data, each new discovery adds a brushstroke to the grand portrait of our planet. The gravity low may one day be fully explained, or it may persist as an elegant enigma, a quiet spot where the pull of the world is just a little bit lighter, inviting us to look deeper, think harder, and never cease to wonder. Beyond the maps and models, the gravity low whispers to the engineers who designed the next generation of satellite constellations. A subtle dip in the planet's pull can alter orbital decay rates by fractions of a percent, prompting mission planners to recalibrate fuel budgets and trajectory corrections. In the same way, deep-sea drilling vessels, when they venture over this region, report unexpected buoyancy shifts that demand real-time adjustments to their ballast systems, turning a quiet geophysical curiosity into a practical navigation challenge. Even the ancient stories of the peoples who first walked these lands echo the mystery of a lighter earth beneath their feet. Folklore from coastal tribes tells of a soft ground where animals would stumble and spirits lingered longer. Modern archaeologists, tracing those legends, have uncovered settlement patterns that avoid the anomaly's core, suggesting that millennia of human intuition may have sensed the subtle difference long before any instrument could measure it.